going to be talking about scalable data-proximate analysis of national water model data in the cloud. I started this work with John Reedy from the HDF group and Julian Chastang from Unidata, and then was joined by this Pangeo community who's really helping us out, and I'll talk about that in just a little bit. So first of all, the reason I'm here is because I head up a sediment transport modeling group in Woods Hole in the Coastal Marine Program at USGS, and we developed this coast model. This is a coupled ocean, atmosphere, wave, and sediment transport model developed by John Warner in our group, and we have hundreds of terabyte output we need to somehow deal with. And you know, like almost every other model, we write our output in these CF-compliant NetCDF files with these stretched vertical coordinates and curvilinear horizontal grids. These are not, going to be GeoTIFF files, right? We have to keep them in these NetCDF files. So we have lots of NetCDF files, and our current, the workflow that a lot of us used in the past was, we do our HPC somewhere on a cloud, not on the cloud, on a cluster that uses InfiniBand because we need fast interconnect, right? So we do our modeling there, and then we move our data over a fat pipe, hopefully, to our desktop computer where we work on it in MATLAB or Python or R. And then we move to a model where we do our HPC on InfiniBand somewhere, and we move our data instead to a server, a file server where we have something like threads running, where then we connect to that and just extract the data we need into our workflows that are still on our desktop computer, and hopefully we have a fat pipe there so we can get the our subset of data relatively quickly. But then we can exchange at least our workflows with other people, and they can use the same workflows, and they're all accessing data from servers like threads, and that's very nice, except that you still need all the compute power on your desktop. And so what we're looking at now, of course, is what everybody else is looking at too, which is doing your HPC somewhere, moving your data instead to the cloud, and doing your analysis and visualization on the cloud where you have all the compute power and you have the storage. And then all you need is a thin pipe back to your desktop. And in this case, we're looking at Jupyter. So we're running Jupyter Server on the cloud, and we have the full Python environment there. And then we're just bringing up a browser on the client side. So the National Water Model, which is a collaboration between the Weather Service, USGS, and some other agencies, has this problem, of course. They're predicting stream discharge and velocity on 2.7 million rivers. And they've got a 250-meter continental U.S. grid, output products on that, and on a 1-kilometer grid. And so 1 month of forcing an output is about 15 terabytes. So clearly, you're not going to be downloading that to your desktop. And so right now, as part of the Big Data project, and the forecast data is being pushed out to Amazon Web Services soon, or just started last week, I think. And the retrospective is out there on the Open Commons Consortium. But there is a problem with all this in that NetCDF files don't work too well on the cloud, and HDF doesn't work too well on the cloud. And the image community has come up with a cloud-optimized GeoTIFF, but we don't really have anything for the n-dimensional data yet. There's lots of things in the running. So we started out, actually, I worked with John Reedy because I heard him give a talk at SciPy last year where he talked about a service that they had set up for HDF files, and we started using that. And then at the ESIP winter meeting back in January, we ran into this other group, this Pangeo group, who was experimenting with another way of storing n-dimensional data if you want to call it a cloud-optimized NetCDF sort of style format. So basically the idea is how do you use the NetCDF data model but put the data onto the cloud in an effective storage format. So this is the project that we heard about at the ESIP winter meeting. It's a really cool project. It's funded partially by EarthCube, partially by Google, and it is a completely open project. You can go to the Pangeo website, clone the repo, add yourself as a collaborator and with your affiliation, and then when they accept the pull request, you become, if you go to the website and look at people, there you are. You're part of the team. And everything they do is discussed out on GitHub issues, as you can see there at the bottom. If you try to take it to Slack, they slap you and say, bring it back so that everybody can see what's going on. And if you and so this is headed up, I should mention, by Ryan Abernathy, who's actually a physical oceanographer at Lamont, with a big team, including folks from Anaconda for the Python side, and a bunch of different domain scientists and technology folks. It's a fantastic group. There's great discussion in this forum. So if you're interested in these kind of issues, I strongly advise you get involved with this, as we did. So not only that, they have a Jupyter Hub running on Google Cloud. And so you can go right now, don't go right now because you have half a MIP. But if you went to pangeo.pydata.org later when you have decent Wi-Fi, you can just get on and start, you sign on with GitHub authentication. They don't even have a whitelist, and you just start using it. And so there's no limit even on the resources. And their philosophy is, if it becomes a problem, it's a problem. But right now, it's not a problem. So, so we're using it. So we moved a bunch of data from NetCDF onto the Google Cloud in this ZAR format, which they had been using. And this is a notebook. As you can see at the top here, it's using actually, so it's running Kubernetes. So it scales with number of users, and it can also scale up the number of processors. So here we've asked for a cube cluster with 10 workers. And so you can actually, if you're doing this live, you can see the workers kicking in, and you can even go to adaptive scaling where you can, or more workers get added as your workflow demands it. So it's a pretty cool setup. And so here we've got 10 workers and 20 cores. And then we open up this ZAR data. We point to the project on Google Cloud, we point to the bucket name, and open it up with Xarray, just as if it was a local NetCDF file or an open DAP URL. And we do DS, and there's our data set. So we've read this data from ZAR, which is a bunch of little, so basically they just take the NetCDF file and put it in little chunks, and all those little chunks go off into objects. And if you want the details, you can watch a great Estep talk on ZAR, an Estep Tech Dive talk. But there it is. So you have the coordinates, you have the data variables, and you can see off over on the right there, in the bottom right, the chunk size. So I have rechunked this data because I know that people are going to want to take time series. So, and then you can just, so you can look at the size of the data. So we're looking at the size of the temperature variable there. This is actually the short-term forcing data. So it's like, actually, if I go back, it's on a 4,000 by 4,000 grid or so. And it's 23, so that one variable is 23 gigabytes. So I've just taken a week just for experimentation. And so that in cell 12 there, I take the mean. And you can see that it takes 18 seconds to do the mean. It would take about 6 hours to download that, on this Wi-Fi here to, your local desktop. And so it's just a picture to show you that we had it. And this is actually a little bonus that you get when you're using this Dask distributed parallel processing system in Python. You get this little dashboard window that you can bring up in another. So while you're in another window, so you're running this notebook, and you pop open this display, and those little bars, each one of those horizontal lines is a different processor, and it's showing, they're going back and forth. You can see all your workers working, and you can see how efficient it is because if there's white space, you know that it's not doing a good job of distributing the work to the workers. As you can see here, this is almost completely solid. Over this 20-second period, every worker was working fully and doing these. The dark green is it's actually loading data from ZAR. The light green is doing the mean over that chunk, and it's putting it all back together. So what we're doing right now is this is a completely cloud agnostic system based on Kubernetes and the Python ecosystem. And so we actually got a little grant from Amazon to explore the national water model data on their cloud. And so we're taking the Pangeo framework that's been implemented on Google and moving it to Amazon. And that's completely in line with the vision for Pangeo. They want it to work on all the cloud frameworks. So we're looking specifically in our proposal, we said we were going to look at these different cloud formats. So we're looking at ZAR, we're looking at this HSDS from the HDF group, and we're also looking at TileDB, which came out of a Microsoft project, and S3 NetCDF, which is coming out of the British Met Office. And they're all taking almost the exact same approach of splitting into a bunch of chunks, putting the binary data into these objects, and then the metadata is some lightweight, either JSON or some kind of lighter weight way to keep track of how everything is put together. And you can And you can read all about that if you want in a really great blog post by Matthew Rockland, this HDF in the cloud. If you just Google HDF in the cloud, you'll find that blog post. So, and we'd love to get more people working. If anybody's interested in the National Water Model data and want to play along with us, please come join us and we'll get you an account on this Amazon system. And so, this is what we're shooting for, right? We're shooting for our HPC. We move this data to the cloud. We have InfiniBand over on the HPC side, and we have Globus, so we can move the data quickly. On the cloud, we're using these technologies of Jupyter Hub, Kubernetes, Dask, Xarray, ZAR, HDS, HSDS, and these others. And also, of course, we could put in things like Threads and ERDAP on the cloud, so that for folks who want to get the data that way, if we get the Java interface to these things developed. So then you're the modeler down there at the bottom. All you need is this thin little pipe in your laptop, and you can launch your simulation. The data goes to the cloud, and all you need is this lightweight interface. I made those slides in the hotel room, with like three megabits per second. So it's totally doable. And if you're somebody who wants to look at this data and do powerful analysis on the data, you can be sitting in the park with your 4G connection, and you're totally fine. And and I think the real goal is in the future, as a modeler, and there's lots of modeling groups, there's lots of modeling output, and I hope that someday it all ends up in the cloud somewhere on Google, Amazon, Microsoft, Jetstream, somewhere, and all this data becomes available through those URLs, and it's all sort of data proximate in this at least very well connected, maybe Internet 2 sort of sense. So there's huge benefits to the cloud, faster, simpler, because you don't have to manage all this stuff locally. Of course, as everybody has said, cheaper. Well, it should be cheaper. It's not always cheaper, as it, with the current pricing models, but it's got to be cheaper in the real sense. Scales with users and demand. You don't have to buy your fancy hardware, software, fast pipe. Local IT departments don't usually like this concept initially, but we're going to be there sooner or later. There's a lot of work left to do, though. Especially, we need to get this n-dimensional data on the cloud thing figured out. NASA is so right now. The big data project for the National Water Model is just like an FTP site, almost, right? Because we've got to take that data. That data is just sitting there in a form that we can't really use. It's on the cloud, but we can't use it effectively in that format. So we got to take it off, and then we got to break it into little pieces and put it back on. And that's so. That's not because they're dumb, it's not because Amazon was not smart. It's just because we as a community, haven't said what we want them to do to make it more effective to use. So they're going to put it out there in NetCDF because they know that everybody can get it and use it in NetCDF. But it's kind of crazy, right? So we're going to get there, but we could use some help in figuring out what the community can really use effectively and what works the best. So please come join us. Join the Pangeo project. Get involved with the Pangeo questions on GitHub. Join the discussion. Thank you very much.
Any questions for Rich?
Do you know whether any of those formats would work with the NexRad radar data, which is kind of specialized to that and these radial observations? Has anybody been looking at that?
All would.
They all would. Okay, thank you.
Hi. I was wondering, there's a number of analysis tools already developed for NetCDF. Would these when you convert to this new format, ZAR or whatever, would these tools work through the portal or work on the cloud? Or would they have to all be rewritten to read the new data formats on the cloud? Stuff like NCO or NCView, all those kind of things.
Yeah, that's a great question, actually. So what I presented was reading ZAR data using a Python interface. We want a C interface and a Java interface, right? We don't want just a Python interface. Unidata right now I know is proposing as a proposal to build ZAR into the NetCDF C library. So in that case, yes, everything would just be handled, and you could have a Java on top of that, but also you could write a native Java interface also. so if that proposal gets funded, if you, reviewers out there, that would be great, right? That's what we want. We just need, we need the language interfaces. We need all the language interfaces for these formats. Actually, that's one of the things that TileDB has going for it, is it does have all the interfaces, but it really hasn't been used too much in our community at all yet, so it's sort of a little bit of an unknown. It also doesn't have the nice X-array, so it's nice to have, you can say OpenZAR and X-array and just have your data there. That's kind of a nice place for a domain scientist, right? So until somebody puts the OpenZAR for TileDB in there, it's not going to get too much testing.